chapter covers the following topics: transmission mode overview, non-time critical communication, real-time communication, and isochronous real-time communication. Completion of this chapter will help you learn how PROFINET handles the full range of real-time communication, including the isochronous real-time communication needed for motion control applications, while at the same time efficiently handling non-time critical communication. As previously mentioned, one of the strengths of PROFINET is that it efficiently communicates both non-time critical data and the full range of time critical data. Non-time critical data is often associated with information technology (IT) processes, but can also be associated with other processes such as device configuration and parameterization. This communication is sometimes referred to as TCP/IP communications, which stands for Transmission Control Protocol Internet Protocol. However, for some types of data, such as audio and video signals, User Datagram Protocol is used in place of TCP. Time-critical data is associated with the real-time RT processes used by many automation devices and the isochronous real-time IRT processes used in motion control applications. PROFINET ensures that time-critical data is handled appropriately by using short communication cycles, partitioning each cycle, and giving this data higher priority. This means that IRT communications are uninterrupted, RT communications are given appropriate priority, and non-time critical data is also communicated. To gain an additional understanding of the timing issues associated with PROFINET's three transmission modes, consider that typical response times for TCP/IP and other non-time critical communication are in the range of 100 milliseconds with a high jitter. Jitter in this context is a variation in the timing of periodic signals. Jitter affects the synchronous reception of data in PROFINET devices. In contrast, RT communication response times are in the range of 10 milliseconds with a low jitter, and IRT communication response times are less than 1 millisecond with a jitter of less than 1 microsecond. Within each cycle of 1 millisecond or less, clock-synchronized IRT data travels in a separate channel from RT and non-time critical data. This, combined with the high data rate of up to 100 megabits per second for industrial Ethernet, ensures that high-performance motion control applications can share the network with standard automation and information technology applications. It also ensures that applications can be scaled up to meet growing customer requirements. Keep in mind the special hardware is required to support PROFINET IRT communication. What do you think? Select all the correct statements, then click Evaluate. The Open System Interconnection (OSI) reference model was developed in 1984 by the International Organization for Standardization (ISO). This model provides a framework for network communications by describing the function of communication software layers. These layers prepare data originating at the application layer for network communication and decode information received via the network for use by application layer software. PROFINET does not use layers 5 and 6, but the remaining layers have the following functions. Layer 1 is the physical layer, which matches the device to the network's transmission media. Layer 2 is the data link layer, which ensures reliable transmission and reception of data. Layer 3 is the network layer, which manages network connections for the upper layers. Layer 4 is the transport layer, which provides error detection and correction. And Layer 7 is the application layer, which establishes connections to the application programs that use the network. Taking a closer look at PROFINET communication layers as they relate to non-time critical communications. Layers 1 and 2, the physical and data link layers, are defined by the Industrial Ethernet Network, which is a fast Ethernet system conforming to the IEEE 802.3 specification. This network operates in full duplex mode, meaning that devices can simultaneously send and receive. Layer 1 ensures that the electrical and mechanical connections match the requirements of the network. Layer 2 ensures error-free communications by splitting data into frames before transmission, checking each frame received for errors, and requesting a retransmission of any frames with an error. This layer also uses Media Access Control (MAC) protocol to handle network device communications. Layer 3, the network layer, uses Internet Protocol IP to ensure that data packets can be routed between sending and receiving devices, even if these devices are separated by great distances and on different network types. Layer 4, the transport layer, uses Transmission Control Protocol (TCP) for data that must be reliably communicated, and User Datagram Protocol (UDP) for data such as audio and video that is suitable for best effort communication. TCP ensures that data packets arrive in order and without error or duplication. UDP is a simplified protocol that guarantees the complete transmission of data, but does not guarantee that data is received in the proper order, is error-free, or is without duplication. The lower layers and associated protocols apply to non-time critical communications for both IT and PROFINET communications over industrial Ethernet. Layer 7, the application layer, must be capable of connecting to a variety of applications, some of which are IT related while others are clearly associated with PROFINET. IT applications rely on a host of higher level protocols, many of which have names that are familiar to anyone involved with network communications. Hypertext Transfer Protocol (HTTP), File Transfer Protocol (FTP), Simple Mail Transfer Protocol (SMTP), Internet Message Access Protocol (IMAP), and Post Office Protocol (POP) are but a few examples. Each of these protocols provides rules for handling specific types of services and file types. Similarly, PROFINET applications use the appropriate protocols for non-time critical communication associated with functions such as device configuration and parameterization, device diagnostics, and transmission to higher level computers. What do you think? Select all the correct statements, then click Evaluate. Because RT and IRT data are time critical, the communication of this data must be done without the delays associated with use of Layer 3 and 4 protocols. Therefore, RT and IRT communication use special protocols and bypass Layers 3 and 4 both during transmission and reception. In addition to reducing response times, this also reduces jitter. To better understand the advantage that fewer communication layers provides for RT and IRT communication, consider what happens as data moves down the layers in preparation for transmission. During this process, protocol information is added to allow for proper decoding on the receiving end. Adding this information takes time, and the resulting data frame, which includes all the protocol information plus the process data, is larger. Larger data frames take more time to communicate and require more time to decode on the receiving end. Transmission times associated with large data frames for non-real-time data are not a problem for IRT data, which has its own communication channel. Recall, however, that RT data shares a communication channel with non-real-time data. In addition to giving RT data higher priority than non-real-time data, PROFINET goes one step further to ensure low cycle times for RT data. This additional step is called fragmentation because each non-real-time data frame is fragmented into smaller frames. This allows more RT data to be communicated in each unit of time. Fragmentation does increase the time it takes to communicate non-real-time data, but this data does not require a low cycle time. PROFINET communication involving non-real-time and RT data does not require use of special switching technology. However, when IRT communication is needed, a faster clock-synchronized switching technology must be employed. This technology is embedded in device hardware through use of an application-specific integrated circuit ASIC, such as a Siemens Enhanced Real-Time Ethernet Controller ERTEC. This technology employs strategies such as fast-forwarding and dynamic frame packing that speed communication. Fast-forwarding reduces data transit time by moving the destination identifier up in the frame. This allows each switch encounter to more quickly determine which data to forward to successive devices. Dynamic frame packing builds on the scheduling and summation capabilities of industrial Ethernet. Scheduling places data designated for more distant destinations ahead of data for closer destinations. Summation combines data from multiple downstream destinations into a frame. Dynamic frame packing goes a step further by dropping off data at each successive destination, thereby reducing the amount of data forwarded. This is shown symbolically in the accompanying graphic. Note that designated data is dropped off at switches B and C, and only data for switch D reaches that switch. Through these combined approaches, PROFINET reduces IRT cycle times, enhancing the performance of motion control applications. What do you think? Select all the correct statements, then click Evaluate. This chapter has provided you with an overview of PROFINET transmission modes associated with non-time critical RT and IRT communication. This information is important to understand the range of capabilities available with PROFINET communication.